Greetings and welcome to a new video. In this video I would like to discuss a mechanical system and electric circuit analogy. We have an electric circuit here and another mechanical system here, and we will discuss and see in that discussion that these two systems will produce exact same transfer function. That is quite interesting when we discuss multi-domain systems and we would like to convert maybe some system in other system parameters, and that is one of the reasons for discussion of this topic. So we will of course do the calculation step by step as I did also in the previous videos, and also do the simulations to verify our calculations, and we will do simulations both in MATLAB and also in Spice. So let's look at our outline before we move on to the discussion. The part 1 will discuss the mechanical system, and part 2 will go in the electrical circuit, and we have also analogy of that mechanical system and also the electric circuit. And part 4, the final part, will discuss the simulation results in MATLAB and Spice. Okay, part 1, the mechanical system. We have the translational mechanical system here, as shown here. And it is a translational mechanical system. The input is the displacement y in here due to some force, and the output is the displacement at this point A, y out. We will determine the transfer function gm for this mechanical system y out over y in, so the output displacement over the input displacement. So it is a unitless transfer function. So how do we start with that? Now we want to develop or set up the equations of motion, and for that we can easily start with the differential equations, and for the mechanical system we most often use the Newton's second law, and that is given by this. So the mass times the second derivative of that mass, motion, displacement, is equal to the sum of the forces. Now, considering now at point A and B a very small mass, because there are no masses given here, there are no any mass drawing, so we can consider that a very small mass, a point mass, very small mass, and then we can then develop this using the Newton's second law. Now we can say at node A the following. We can say the mass A times the second derivative of that motion is equal to, now we need to now sum all the forces. We have the force due to that damper, B2, and also B1 will fight back, and also we have the K1, which is the spring, will also fight back. So we have three forces. So B1 and B2 and also the K1. So B2 times the difference in the velocity is actually the force by that damper. And it's a minus sign because it is fighting back. So it is minus B2 times the velocity, so the first derivative of that y out, minus the first derivative of actually this one. So the difference between these two velocities is actually the actual velocity of that B2. That's actually shown here. That's also the reason why we have this y2 here, to designate that part as a motion. Now B2 do the similar thing. Of course, y out and a y in is there required to determine the difference in the velocity. So it is then minus b1 times the difference, so it is then referred to what we do, our motion y out, minus the motion, the velocity at the top y in. Now we also have the spring, which is also in similar form, but then you use the spring constant times the difference in displacement. That is then y out minus y in. That is those are the formulas, the generic formulas for spring and a damper. For the spring you use the spring constant times the difference in the displacement, and for the damper you use the damper coefficient times the difference in the velocity. Now this is now the transfer function, the differential equation for that part, only for the point A. Now, considering the mass 0, because we just assume something, but now we need to approach that to 0, then this will be 0. And everything is, of course, same for the right-hand side. Now we can also say, let's then multiply the left and right-hand side by minus 1, you will get this. Okay. We do the similar for the node B, and node B we have the following. Again, assuming mass B very small, and then set up the equation of motion using Newton's second law, what we see is at this point K2 is fighting back and B2 is fighting back. So we have actually two forces there. That's actually shown here. And again a minus sign to fight that back because it's fighting back, and minus B2 it's also fighting back. In this case the Y2 is only displacement here because this is a mechanical reference point, so it is just 0. So that's the minus K2 Y2 and a minus B2, and again the difference between the motion here and the motion there. And since we consider now B2 here, this is what we take first minus that velocity there. That's actually shown here. Now considering then this mass B and B0, and also take that here and multiply now left, right, and the left and right hand side by -1, you will get this expression. So we have the equation number 1 and also equation number 2 here. So we have already developed two differential equations for point A and point B for this complete system. Now the next step is using Laplace transform to work out these two differential equations more easily using the transformation of ddt to s. And we assume then, taking the Laplace transform of 1 and 2, we assume the 0 initial conditions. So we assume all of the conditions, so it is at steady state, there are no any displacements before we, let's say, disturb this system. Now we get for the first equation here, so we just replace ddt by an s, exactly the same here as shown here, and that will be then equation number 3, and a similar form you get from equation number 2, this, and that will be then equation number 4. So that is the Laplace transform of 1 and 2 and 3 and 4, equation number 3 and 4. Now we need to have our final form y out over y in. And I don't like to have the y2 here, so that is a parameter I need to replace or substitute. So for that we can rewrite equation number 4 such that the y2 is expressed in other parameters or other variables we want. Now, I have now this, so I will now take out this parenthesis of b2 times sy2 and then b2 times minus sy out, that's actually shown here. And I can now rewrite this such that I have the y2 together and y out together. So I will place this part to the left side will be a plus, and I have this expression. I can now rewrite this and equate y2 in the rest of the parameters or the variables. And this is now equation number 5 I can now use in the equation number 3. So let's do that. But before we move on, let's also rewrite equation number 3, because that's also something we need to work out before we can easily substitute this equation number 5 in here. So we work out the parentheses, so b2 times sy out and also b2 times minus s y2, etc. For the rest, you will get this expression. Now collect the terms, so y out and y ins, etc. And you will have this expression. And then in addition, you can now see there is a minus b2s y2 here. Now let's then substitute this 5, equation number 5 in here. So in equation number 6, I substitute equation number 5. Then you get the following. You see that already is not good enough, so we need to move on. That is the following. We can say the left hand side and the right hand side we can multiply by k2 plus b2s. And before we do that, we can also replace this minus b1s plus k2 times y1 to the left hand side. We'll have this one. And then what I just said, we'll multiply that to get rid of this fraction. Now we have this expression. That is the final, in this form, the final form. Okay, now what we do next is you can now also work out the parentheses here and see the s squared and the s terms and also the constant terms. We see an s squared term also here, and there is also some s squared term there when I work out the parentheses. So let's do that. So this is now the last form we had. If I now work out this parenthesis, I will get b1 times b2 s squared, but also get b2 times b2 times s squared. It will be then b2 squared s squared. But I have it also here. So that will be then, that cancels, so that goes. And then I have the final form in this form. And then what? Now we can then say, let's also collect all the s terms together, because we have an s term here and an s term there. So let's all take that together. So work out this parentheses and then make this complete coefficient only for s. So left side just stays the same. We only do the business on the right hand side. The next step is now really crucial, because I would like to have an expression where we see some fractions and then easily recognize the poles and the zeros easily. That is actually one of the objectives, to write down a transfer function nice form. Now this can be done in this format. I can divide the right hand side and the left hand side by k1 times k2. Now this down here you can see easily. So this term is divided by k1 times k2. Also this one completely, and also this one. I also do it here, but I do it in a specific form. I say I will do it for this part, only divide by k1. And for this part, I divide only by k. That's perfectly fine. I can do that. So I will take only the part I require. And that's the reason for doing that is the k1 is now 1. And k2 here is then also 1. So now I will get this nice expression. And I recognize directly what happens when this part is 0. And I can then pinpoint the zeros or the poles easily. Now for that, I need also work out and do some steps in addition. Now the left side stays still the same. This is exactly the same as before. The first part, the coefficient for before the s squared, this is 1. I now split this in 2 parts. The reason for that, doing this, is the following. I want to have an expression also here in this format also, such that I can recognize this also easily later. So I want to have 2 fractions or 3 fractions where necessary. And what I see is I have the b1 and k1, and I also have b2 and k1 here, and I have only split at b2 times k2 out of it. And if I now combine this, the first, the second, and the fourth terms, I can make that also a fraction. And that's very nice. And of course, k2 and k2 cancel, so I will get b1 or b2 over k1 times s. So I have now this expression. Now this is now much easily to read. And if I now work it out, I have now this y out or y in will be then this, that will be go in the numerator over this, which is then in that bracket, which is then our denominator. Now we have a second order system with 2 zeros and 2 poles. The zeros are quite easily determined. You equate that numerator 0 and you will get minus k1 over b1 for the first 0. Another 0 is minus k2 over b2. But the poles are a little bit difficult. So you need to set this denominator to 0 and then have this equation, which is given in symbolic form using that quadratic formula solution. What you do is then for pole 1 and pole 2, for pole 1 you take actually the one with the plus sign in front of this square root, and for the pole 2 you take the minus 1. And the rest are exactly the same. So this is just symbolically given. If you have a calculation, want exactly the poles, you just substitute the value for k1 and k2 and b1 and b2. You have your poles and also your zeros. Okay, this is then the final result for our mechanical system transfer function. Input y in, which is our displacement, and output is also y out. That's also displacement, so we have no unit in our transfer function again. All right, moving on to part 2, electric circuit. This is our electric circuit. We see a resistor R1 and C1 in series, and we have also R2 and C2. Those are in parallel. The input is a voltage, and output is also voltage. The same thing, voltage. And we would like to have the transfer function of a GE, V out over V in. Now, how do we work out the solutions here? In this case, we don't have to set up the differential equation. It is possible, but it is much faster in this case because there is a ratio to do the voltage divider rule. Now, what is it saying? The voltage divider rule is saying the following. If you want to have a voltage division between some part and another part, so output and input, you can do the following. You can say output voltage over the input voltage is the output impedance seen at that node to ground, divided by the total impedance seen by this input, which is actually what we say here. So R1 plus the reactance of the C1 over R1 plus reactance of the C1 plus this impedance, which is the parallel combination of R2 and C2, which is actually shown here, XC2. X is the reactance of a reactive component, in this case the capacitor. It can be also an inductor. And for a capacitor, or a capacitor reactance, the general formula is given by 1 over SC in the Laplace domain. Now, if I now move on, I can say, specifically R2 and the C2, I can say R2 and parallel with the C2 is XC2. I can write it down in mathematical form, this one, R2 times XC2 over R2 plus XC2. Now, if I now substitute this 1 over SC specifically for C2, I get this. Now, if I work it out, just multiply the numerator and denominator by SC2, I get this one. This is a nice expression to substitute it in here. That's what we do. Also substitute for C1, this XC1, this expression specifically for C1. Now the next step is I want to get rid of the fraction, so I don't want to have that 1 over etc. So let's then multiply the numerator and denominator by SC1. Then you will get this. So this will get an SC1, this will be a 1, this will be a 1, this will get an SC1, so R1 times SC1. This is exactly as before, so that doesn't change. It changes something, but it is not really simplified. Now the next step to simplify this, because this is also a fraction I want to get rid of, so I will multiply the numerator and denominator by 1 plus R2C2. So this will be then multiplied by this part, also this, and I only get R2C1 as a separate part in the denominator. And the final result is shown here. That is our electric circuit transfer function V out over Vn. You can see the result here for the transfer function. Now for the zeros, it's similar. It is minus 1 over R1C1 and minus 1 over R2C2, two zeros. And the poles, in a similar form, you need to set the denominator to 0, and you will get that. This is the equation we use also for quadratic formulas. And again, pole 1 is the one with a plus in front of the square root, and the pole 2 is the one with the minus sign. Okay, that's now for this electric circuit. Now let's go now to part 3, which is the analogy between the mechanical system and an electric circuit we have discussed so far. This was our mechanical system. This was a transfer function. And this is the electric circuit with this transfer function. What do we recognize? Let's look at the elements. Let's compare the elements in this transfer function. If I look at the elements, I see the following: the resistive and the capacitive elements, because the B's and the R's are resistive. So the resistance is resisting the current flow, and the B's in damper is also resisting the motion. So we can say the following: the damper B in the mechanical domain is similar to the resistance R. And the it is resistive. And the capacitive, it is actually, if you compress a spring with a constant K, it is sort of the compressing or charging up a capacitor in electrical domain, which is the capacitance C. And by analogy, you can say the B, the value coefficient, is similar to R in the electrical domain. And a K in the mechanical domain, translation mechanical domain here, is similar to 1 over C in the electrical domain. You might ask why. Now let's now compare also the transfer functions carefully. The denominator of the mechanical transfer function is B1 over K1, the first one. And if I look at the first term, it is R1 times C1. So B1 is similar to R1. And C1 is similar to 1 over K1, or K1 is similar to 1 over C1, similar to B2 and K2. Also here, and also there, and also here. So exactly the same as in each form. But you need to remember, of course, if I do this R1 and C1 and R2 and C2, you will get exact same, let's say, expression for the mechanical domain. But this will be then have a different index. So you need to be exact same in this indexing also. Why? That's also the next discussion, because comparing the systems, mechanical and electric system, we have through and across variables. What does it mean? If I apply a force here, that force is the same for K1 and a K2, and it's exact same forces applied to these two elements. The force here and the force here is different, but the force for these two elements is exact same. This is similar to say the current here for the R1 and C1 is exact same because it is a series of two elements here. So I need to say, to compare that easily, I can use the same index as 1 and 1 for also the electrical domain. So I can say for this system, the through variable is the current electrical domain, and the through variable is the force for the mechanical domain. That's the reason for having this parallel, but this in series. But the across variables in a mechanical domain is the velocity. And the velocity here is different than the velocity there. So that is the across variable, and the voltage here is also different than the voltage there. But it's across that you have exact the same voltage difference, and across that you have exact same velocity difference. So that is the reason also to have this series here connection is similar to the parallel connection in the electrical domain. This is very mandatory to understand this. Otherwise you mix up something and you get different indexes and you think it is not similar, which it actually is, but you started with it wrong indexing. Okay, so through variables and across variables are very important to compare this easily. Now these are some tables to summarize our through variables and across variables for physical systems. Very important if you do a lot of dynamic system modeling. We have electrical domain analysis done, and also mechanical translational, and we have seen through variables the current, and also for the mechanical translation the force. But if also charge, if you talk about the mechanical system, also the voltage difference or flux. But if you go, for example, the mechanical domain, but then rotational, the torque is also a through variable. So instead of force, you could have a torque, or angular momentum instead of a translational momentum for the mechanical system, mechanical translation system. So you also have a fluid or thermal system, so you have a lot of other domains. If you have a combination of, let's say, a thermal domain and a mechanical domain, and then you will like to convert that, the easiest way to do that is in energy domains and power. So that's also shown here what the relations are for the energies in each domain, each system. This is just to summarize. I won't go through the details. So if you want to see this in great detail, you can just pause here and then take a picture of this one. Okay, let's then go to part 4 and discuss the simulation results. Now let's first bring up the MATLAB code. I have generated this is the MATLAB code. So you see I just defined first the Laplace parameter. Mechanical system, just made up some values for the B1, K1, B2 and K2. And also set up the transfer function according to our discussion. Okay, now we also have the electric circuit. We said R1 is similar to B1, but C1 is similar to 1 over that K1, and a similar form for R2 and B2. And a transfer function here. An input-output signals, so this input displacement 10 meters. I just selected something. And we have also the input voltage. I also set the exact same to compare it easily, 10 volts. And Y out is the output displacement, and the V out is our output voltage for our electrical system or electric circuit. Now this is the if I run the script in the command window of MATLAB, I get this. You see GM. This is our mechanical system transfer function, continuous time transfer function. This is of course not really easily read, so I will use minimum realization function of MATLAB. GM is min real, and then I will get this expression, which is much easier to see. It is second order, 2 zeros, 2 poles. You can already see that. You can do this same also for GE, which is an electrical transfer function. Again, use min real, you get this one, which is recognizes this transfer function is exact same as this one, which is not a surprise. We already discussed this, so it's exact same transfer function. Nice. And for step, you use these two commands for these systems. Okay, let's now look at the response to a step input displacement of 10 meters in MATLAB. This is the response due to step input displacement of 10 meters. So 10 is the orange input, and output is the blue one. You can see the minimum value, some labels here. So this is the mechanical system and this is the transfer function. This is the minimum value 0.27 at 0.27 seconds with a value of 4.5 approximately meters. And for other specific times I also have here for 3 and 6. I label this in order to also compare it with the electrical circuit shortly. Now let's also go to the step input voltage of 10 volts. Then for the specific it must be due to not to due. There's actually some mistake here in the naming. And we have now an electrical circuit, this one, and this is transfer function. This is the minimum, exact same time for a value at the 3 and also at 6 seconds. So that is all same, so not a surprise. But now the things will get interesting where we also compare it in Spice in a different simulation. So response to a step input voltage of 10 volts, but in Spice. So I just developed this circuit, exact same values. Of course, C2 is equal to 1 over K2 and R2 is B2 and R1 is B1 and C1 is 1 over K2. This is the response. The red one is the input, 10 volts, and the blue one is our response. You see actually at 3 seconds and also at 6 seconds it is quite similar to what we have seen in the MATLAB. But this is not accurate. So we need to tackle this and also see this in more detail. The reason for this non-accuracy is because this is not really sampled accurately in that simulation. So in order to do that more accurately, you can zoom in at the part. So I do again the simulation in Spice and zoom in this part. So I just plot not from 0 to 11 or 10 seconds, but from 0 to 1.3 or 1.4. And then just zoom in the part. Then I have more samples for my location. You see it's 4.5 volts actually at 0.20 seconds, approximately 27 seconds, which is actually also what we had. So this is actually zoomed in version. And now using the zoom in version, you can compare that this is indeed the correct result. That's also one of the important things when you do simulations. Be careful with the sampling time and also other calculation methods to verify your results. All right, this is then for this example about a mechanical system and electric circuit and discussing the analogy between those systems in different domains. And we also discussed that the exact same transfer function is produced even though we talk about 2 different domains, which is of course really important since we also have multi-domain systems in actual world. If you have any questions, comments about this exercise, this video discussion, please let me know and I will try to answer them as soon as possible. See you next time in another interesting video. Take care.